Here we are in topic 5, where we move from an introduction to descriptive statistics and a look at experimental designs to the world of inferential statistics. The use of statistics to critically analyze and interrogate individual data sets and compare multiple data sets. And we'll begin this adventure, if I can use that word, with examining the normal distribution. The normal distribution is a special type of even distribution with the properties that we'll be examining in this topic here. They have special properties and they form the foundation pretty much of all useful statistics that most of us will use in our working lives. Underlying this topic 5 discussion of the normal distribution is this interesting data set that was collected at the Growling Frog Vineyard in 2014. We recorded the temperature in the canopy, so the foliage of a grapevine in this vineyard for each day during March in 2014, with temperatures logged, I think it was every 5 minutes, it may have been every 2 minutes. We logged the temperature during the night and during the day, but we're looking specifically here at daytime temperatures. I've made a histogram of this data set. The full data set is available to you on the subject homepage. Histogram of this entire data set, and you can see the temperatures range from around 8 up to nearly 50 when the sun was shining directly on the loggers, with most values around the mid-20s, which would be normal for that time of year. There was a heat wave last year which resulted in those very, very extremely high temperatures. Just looking at the graph casually, you can see it's quite evenly distributed. And we'll be examining this even distribution and discussing why it's a normal distribution in this topic. So I want to examine now this data set in more detail and this distribution in more detail. If you're following on with the slides for this topic, you will see I've skipped over a couple of slides looking at the sample distribution. We'll explore those more in topic 6. But here I am again looking at this even distribution. And I've titled this density curve. Density curve really is another name for normal distribution. The density curves have very special properties, and I'll show you what they are. First of all, let's make the area. I've put a curve over this histogram here. It's quite a jagged curve. Let's pretend it's a nice smooth curve, nice even symmetrical curve, where it's rising gradually on the left, peaking in the middle, and then slowly dropping again as a mirror image on the other side. Let's say the area underneath this curve, bordered by the black line here and the x-axis, let's say that area equals 1. When we do this, the curve takes on special properties. If we select two values, any two values in this data set, the area encompassed between these two data points will equal the proportion of all values that were found between these 2 points. Let's, for argument's sake, take the temperatures 18 and 26. All right, I put a red line from where 18 is on the x-axis going vertically up to meet our curve, and the same at 26. The area under the curve between these 2 points, assuming that the area under the entire curve is 1, so whatever the area, proportional area is between those two red lines, will equal the proportion of all recorded values that were found between 18 and 26 degrees. Let's say that the area between these two lines is 0.25. Remember, the entire area is 1. So in other words, a quarter of the entire area under this curve is found between these 2 points. If that is the case, then 25% of all recorded values, all recorded temperatures which were logged in the canopy of this grapevine, would be between 18 and 26 degrees. This is statistical dogma. It's mathematical, a universal mathematical fact if the data set we're looking at is normally distributed. We summarize normally distributed data with the mean and the standard deviation, and we do it like represented here. We put an N, which says normal distribution, bracket, the mean, comma, the standard deviation, close bracket. You can see here we're referring to the true mean and the standard deviation of the true mean, or the population mean and the population standard deviation. Not sample means, not sample, standard deviations. Standard deviation and the mean of the population here. And this is how it's always summarized. So if I read that, I'd know straight away that the data is normally distributed, what the mean is, and what the standard deviation is. And a reminder, all normally distributed data will have a symmetrical, single-peaked, bell-shaped or even distributed histogram. How do we in fact calculate the area under the curve? Well, it's governed by this horrible formula here, which you'll never need to know. But the area under the curve can be calculated. But most of the time we don't need to. We just need to use this fact that the proportional area under the curve equals the proportional number of observations found between 2 points. With normal distributions, the standard deviation governs the spread of the curve. The larger the standard variation, so the average difference between each data point and the mean, the greater that value, the more spread out the curve will be. The lower the standard deviation, the narrower the curve will be. So this curve on the left would have a larger standard deviation than that on the right. Representation of this, the series of 3 curves in the top left here all have the same mean. So the peak is at the same point for each curve. However, their spread is different. The red curve would have the largest standard deviation and the purple or blue would have the lowest standard deviation. Whereas in the bottom right, we have 3 curves which are equally spread, so their standard deviation would be the same, but their mean is different. You see their peak is in a different spot. Here's the kicker with normal distributions. They have this fantastic property. 68% of all observations will be found 1 standard deviation either side of the mean. So if we had the mean and subtracted 1 standard deviation from it and added 1 standard deviation from it, the area between those 2 values will encompass 68% of all observations, or the area under the curve would be 0.68. 2 standard deviations either side of the mean encompasses 95% of the observations, and 99.7% fall within 3 standard deviations of the mean. So this is in normally distributed data sets, and we can use this to prove if our data set is normal. And you can actually do this with the data logger, the data for the Growling Frog Vineyard. The data set is available to you on the subject page. And if you subtract 1 standard deviation either side of the mean using that spreadsheet, and then find the number of values between those 2 temperatures, you'll see that it is approximately 68%. Likewise, 2 standard deviations either side of the mean encompasses pretty close to 95% of all the temperature readings taken at that vineyard, which goes a long way to prove that that data set is normally distributed, and also proves that normal distributions do occur in real life. So I've put up a spreadsheet with the workings out to calculate the number of data points which are encompassed, the temperatures within this data set, which encompass 68 and 95% of the data points. So that's 2 standard deviations either side of the mean. You'll be able to find that spreadsheet in the topic 5 folder on the subject page. I've represented them here on the graph, the two red lines being one standard deviation either side of the mean, and the green lines representing the temperatures, which are 2 standard deviations either side of the mean, when 95% of values are between. So 3 standard deviations either side of the mean, the lines would be even further along, encompassing an even greater spread of temperatures, as one would expect, because it includes all but 0.3% of all the data values in this data set. And what you'll see from the spreadsheet, or if you calculate it yourself, is that 1 standard deviation either side of the mean is around 24 degrees, and the standard deviation is around 8 degrees. So 1 standard deviation either side of that mean would be 16 degrees and 32. Therefore, 68% of all data points would be between 16 and 32 degrees, or a proportion of data values of 0.68, which means the area under the curve encompassed by these two temperatures would be 0.68 if we have the entire area equal to 1. So the beauty of these normal distributions now is we can convert these proportions into probabilities. And we can say directly that if the proportion of values between these two temperatures, 16 and 32, if that equals 68%, then we can say the probability of arriving at this vineyard when the temperature is between 16 and 32 is 68%. If we had an interval, 2 temperatures which encompass 95% of values, we'd say the probability of arriving at this vineyard between these 2 temperatures is 95%. So this is the beauty, we can convert these proportions directly into probabilities. Unlock the full power of the normal distribution, how we can convert area under the curve to proportion of values and in turn that to probabilities. What we do is we standardize our observations. We do this, we standardize, what we want to do is convert our numbers in our data set such that 1 standard deviation equals 1 and the mean equals 0. And to do this, from each data point we would subtract the mean, in this case the population mean, and divide by the standard deviation of that population mean. And if one does that, it's very quick to see that the mean would then turn to 0, because if you subtract the mean from the mean, you would get 0, divide by the standard deviation, that's still 0. If you have a data point which is 1 standard deviation greater than the mean, that would equate to 1. So let's say, for example, let's take growling frog temperature for an example. The mean is 24 and the standard deviation is 8. If we add the standard deviation to the mean, that gives us 32. So let's say x is 32 and we want to standardize that value. 32 being 1 standard deviation greater than the mean. Therefore, to standardize it, we would subtract the mean and divide by the standard deviation. So we have 32 minus the mean, which is 24, which gives us 8. Divide 8 by the standard deviation, which is 8. 8 divided by 8 is 1. Therefore, we've standardized it such that the standard deviation equals 1. If we had 2 standard deviations greater than the mean, that would equal 2. In this case it would be 40, so 40 minus the mean, which is 24, gives us 16, divided by the standard deviation, which is 8, gives us 2. So we standardise it such that we can see the number of standard deviations greater than or less than the mean for any value. So if something was 1.5 standard deviations greater than the mean, its standardised score would be 1.5. These standardised scores or values we call z-scores. And once we've standardised them, we can use these conveniently pre-created tables, which someone's done some very hard work through mathematical time to create, and for any value of z we can get the probability of a data value being less than that. Let's see how it works. And here is the table that allows us to convert these standardized numbers into an area under the curve. And remember, with normal distributions, we make the area under the curve equal 1. So we get our z-scores, and this z-score then corresponds to an area under the curve to the left of that value. So here I've got an excerpt from the table, and it's called the standard normal probabilities table, and the reason for that will become obvious soon. This is available to you in your formulas and tables guide on the subject page. The z value is found in the left-hand column. We get the first number and the first decimal place, and then the second decimal place of the z-score is found in the top row. So for example, the very top row of numbers here correspond to z-scores of -3.40, -3.41, -3.42, etc., all the way to -3.49. Then you move down to the next row for -3.3. This table goes all the way from -3.49 up to +3.49. These numbers with 4 decimal places are the area under the curve to the left of that value. So using -3.40 as an example, the number that corresponds to is 0.0003. That means that is the area to the left of that z-score. And remember now, this is not just a normal, because with a normal distribution, an area converts to a proportion of values. So 0.0003 as a proportion of the values are found to the left of this number. And this can be converted to a percentage. So 0.03% of values will be found to the left of this number. And also, the probability of getting a number less than this z-score would be 0.03%. So it gives us the probability of having something less than that z-score as well. If we want to work out greater than, we subtract that number from 1. So that gives us the area to the right of that value, or the probability of getting a data point greater than that z-score. So an example use of this would be, we want to know the probability of arriving at Growling Frog Vineyard when the temperature is less than 40. We want to know what's the likelihood we're going to get there and the temperature is going to be really nasty during March, because that may change whether or not we may have certain functions there or do certain analysis that time of year if the probability of the temperature being less than 40 is too low, or in other words, the probability of being over 40 is too high. So we can use our data set and these normal distribution rules to actually work out what is the probability of arriving at this vineyard when the temperature is less than 40. And what we do is we convert this 40, we standardize it, creating a z-score, and then use the table to determine what the probability of arriving at this vineyard is when the temperature is less than 40. With this spreadsheet from the subject page, you can do these calculations yourself. First of all, you've calculated the mean and standard deviation already. So we have 40, we need to standardize that to create a z-score. So we get 40, we subtract the mean and divide by the standard deviation. And that gives us our z-score, and that gives us 1.98. We then go to the standard normal probabilities table and look at what area under the curve is found to the left of 1.98. That number, if you go to the table, you'll see is 0.9761, and that converts straight to a probability. So the probability of arriving at this vineyard with the temperature less than 40 is 97.61%, so quite highly likely. Now we can take it further and ask, what's the probability of arriving at this vineyard, Growling Frog, when it is between 20 and 25? Well, this is just a simple matter. We get the area under the curve to the left of 25 after it's been standardized to a z-score, area to the left of 20 after it's been standardized to create a z-score, and subtract one from the other, and that gives us the area under the curve between these two values. And as we saw before at the very start of this lesson, that can be converted directly into a probability. So we get the area under the curve between those two values. That would give us the probability of arriving at this vineyard between those two temperatures. Simple. Okay, let's look at another example here. This one's from a examination that took place of adult men in the US between 1976 and 1980, looking at the heights of these men, men aged between 18 and 24. And what we're told is the data is normally distributed with a mean of 70 and a standard deviation of 2.8. The question is, how tall must a man be to be in the lower 10% for men aged 18 to 24? So what is the tallest a man can be such that, well, what height must you be less than to be in the lowest or the shortest 10% of men aged 18 to 24? The classic example of using this Z-score technique in reverse. So we're essentially given a probability. We're given an area under the curve to the left of a Z value, 0.1, with a probability of 10%. So all we need to do is go to our Z-score table, our standard normal probabilities table, and look for an area under the curve of 0.1 and see what Z value that aligns with. And if we do that, we see that it aligns with a particular Z value. And over this slide and the next, we see the calculations based on this, rearranging the standard formula to solve for a sample mean, or I shouldn't say a sample mean, a value, a height of that a man must be to be in the lower or the shortest 10% for all men in this sample. And we can do this because this value of Z that we've taken from the table that corresponds to the area of the curve of 0.1 is a standardized height. It's a height that's been standardized by subtracting the mean and dividing by the standard deviation. To use these techniques, we have to remember that our data must be normal. The simplest way of doing that, and a very valid way, is looking at the histogram and seeing that it's even. That is still done at a very high statistical level as a proof that the data is normal. In topic 7, we'll be looking at some sample sizes that we can use to judge whether or not our data can be used for these sort of tests, and how much skewness we can handle. But seeing a nice even distribution in our histogram is a very good way. The best way is using a normal quantile plot, and we'll examine these more further in topic 8. So we'll leave it until then. These next few slides are based around that technique. So the question that we started with, are horses with a high cholesterol level, that greater than 210 milligrams per ml of blood, and a greater risk of heart attack after exercise? And to do this, I'd like you to calculate the probability of a horse in each of the groups, group 1 and 2, having a cholesterol level greater than 210, and see which one has a higher probability. Are they different? Are they extremely different? In topic 7, we'll see how we can determine if they're statistically significantly different. But at the moment, let's just get probabilities for the two and see if they're different. We do that just using 210 as our value of X. So we'd standardize 210, get a Z value, and get the probability based on that.